Hello everyone, and welcome back. Today we're going to continue our explorations of ordinary differential equations, but we're going to be taking a break from analytical methods and solving first order equations and focus more on numerical methods. The reason for this is we can't always try to develop a method for every single differential equation. And even if we do, we're probably going to encounter some special functions that we've never encountered before anyway. So a very useful thing to discuss is numerical methods for solving ordinary differential equations, and hopefully we will be able to control the amount of error that these numerical methods have, and therefore we can practically obtain a numerical solution to any ordinary differential equation and have it have any level of accuracy for which we desire. So the differential equation that we're going to be looking at is the typical first order equation. This can be linear, nonlinear, homogeneous, inhomogeneous. It doesn't really matter here. And we're going to assume that it has an initial condition of yx0 is equal to y0, where x0 and y0 are real numbers, hopefully in the domain of existence for this solution. So what I'm going to begin by doing is rewriting y prime of x as a quotient of differentials. So we know we can write y prime of x as just the quotient of differentials dy divided by dx, and we know the definition of dy over dx, at least the forwards definition, is the limit as delta x approaches 0 of y of x plus delta x minus y of x all divided by delta x, right? So this is the forward difference definition, because we already know that there are other definitions for derivatives, backward and also central, and several others as well. But for the methods that I'm talking about today, the forward difference will do just fine. So let us assume that we don't take the limit as delta x approaches 0 and just take delta x to be arbitrarily small. Then what we have is that this is going to be an approximation, in particular dy over dx, is approximately equal to x plus delta x evaluated into y minus y of x all over delta x, where delta x is arbitrarily small and positive, right? So we have this approximation for the derivative of y with respect to x, which is the left-hand side of our initial value problem. So what I'm going to do is I'm going to substitute this into that expression, and I'm going to solve for this y of x plus delta x term. So when I have that, I'm going to have the following. So we have the y of x plus delta x is going to be approximately equal to y of x plus delta x times f of x, y of x, right? And we have this particular statement. So notice what we have here is we have y evaluated in the present plus some real number times f evaluated at the present domain value, the present range value, and what we have here is the value of y in the future, in particular delta x in the future of the present. So this is actually referred to as Euler's method for solving numerically differential equations, right? So let's sort of walk through theoretically of how this method works. Keep in mind we have y prime is equal to fxy with the initial condition that yx0 is equal to y0. And what we're going to do is we're going to let x1 be defined to be equal to x0 plus delta x. We're going to define x2 to be equal to x1 plus delta x, which is the same as x0 plus 2 delta x. We're going to have that x3 will be equal to x0 plus 3 delta x, and this is going to continue all the way down to xn plus 1 is equal to x0 plus m plus 1 times delta x as a general way of calculating the nth domain value in the future. Okay? So, is this really going to be an accurate method? Or actually, before we dive into the accuracy of this, let's sort of walk through how this would go. So what we would have is that y of x1 is going to be equal to y of x0 plus delta x times f of x0 times y of x0, which we're just going to abbreviate as y0 just to keep things nice, right? So that's just y of 0. Right? So that's our initial condition y value, that's our initial condition x value, initial condition y value. That x0, y0 is going to be evaluated inside of f times our domain step, and then added our old y value, and then we're going to have our new y value at the next time step or domain step. And then if we want the next value in the future, x2, we're going to have y1 plus delta x times f of x1, y1. So these values, these y1, x1, and y1, these were found in some sense in this previous step. And then we can, for example, go to yx3, which is y2 plus delta x times f of x2, y2, which was found in the previous step, and we can go all the way down. For example, we have x0, x1, x2, x3, all the way down to the final x value, let's say xf, and that will cover your domain for your solution, and hopefully you can get some sense of what that curve is by connecting those dots to get your numerical solution. So what degree of accuracy is this going to have? Because it is a numerical solution, but it's possible that the actual solution is slightly different, and hopefully it's not very different, else our interpretations based upon it might be very misleading or completely incorrect. So what we're going to do is we're just going to recall the Taylor series from single variable calculus. So let's recall the Taylor series. For example, some function f centered at some point x in the domain of f. So when we have that, and we perform a shift, what we're going to have is that y of actually instead of f, I'm going to call it y, since we're using y here. So y of x, y of x. So y of x plus h will be equal to y of x, that's the 0th order term, and then plus y prime of x times h, or delta x, I guess you could say. And let's actually keep uniform, let's use delta x. And then we're going to have plus y double prime of x times delta x squared over 2 factorial, plus the third derivative of y with respect to x, times delta x to the power of 3 over 3 factorial, and so on, right? And this delta x term is just going to be equal to x plus h, or x plus delta x minus x, for any x in the domain for which you're interested. Right, so it's the distance between time steps, I guess you could say, if we're talking about x being time. Right, so that's our Taylor series. So what I'm going to do is I'm actually only going to look at the first order approximation and then treat this as an error term or an error bound. Right, so when I do that, I'm going to have that y of x plus delta x will be equal to y of x plus y prime of x times delta x plus y double prime of psi times delta x, the quantity squared, over 2 for some real number psi in the interval x comma x plus delta x, right? And the existence of this psi comes from Taylor's theorem, right? So there exists this number psi associated to Taylor's theorem. Taylor's theorem, not Taylor's series. Okay, and you probably would remember that from single variable calculus, of course, right? So if that is the case, what we have here is y of x plus delta x is equal to y of x plus delta x times y prime of x plus some delta x squared ordered term, right? So that's the second order and higher order terms of that Taylor expansion. And from here, what I'm going to do is I'm going to divide both sides by delta x. When I have that, and I solve for y prime of x, I'm going to have that y prime of x will be equal to y of x plus h, or delta x, let's say, y of x plus delta x minus y of x all over delta x plus, instead of delta x squared, now we just have delta x because that canceled with that 2. Right? So once I have this, then we can say that y prime of x is approximately equal to y of x plus delta x minus y of x all over delta x. And since this is an approximation, one can say what is the order of the approximation. According to that term, that's a first order approximation for y prime of x. So since that is a first order approximation for the first order derivative, and you can similarly prove that the backwards difference definition is also a first order approximation, and moreover the central difference is second order, then from this we can say that y of x plus delta x is equal to y of x plus delta x times, and keep in mind y prime of x is just another way of saying f, because keep in mind y prime is equal to fxy, so those are the same exact thing. So this statement here, which again is called Euler's method, is first order accurate, or it has first order accuracy. First order accuracy. Right? So of course, if you have a second order accuracy method, of course it's going to produce more accurate results, but it's a starting point for the conversation. Let's work through a numerical example to sort of see how Euler's method works, at least by hand. So let's assume we have this particular first order differential equation, y prime is equal to x squared plus y squared, with the initial condition that y of 0 is equal to 1. We clearly see that we have a nonlinear term here, but you should recognize this particular type of equation as possibly a Bernoulli's equation, or possibly even a Riccati's equation, right? So this analytical solutions do exist, but let's assume that you don't know how to find them. So what we're asked to do is to numerically solve this. That is, we're possibly going to have an error, hopefully controllable. In particular, we're going to be using an Euler's method with a delta x step of 0.01. Of course, if you want to make that a little bit more smaller, your accuracy will be a lot more accurate, but you're going to need a lot more iterations of the Euler's method to cover the same exact domain as this larger delta x value. So there are some pros and cons to making your delta x super small. It just takes a really long time. So what is Euler's method? So let's just recall. So Euler's method is y of x plus, in this case, 0.01. This is going to be equal to y of x plus 0.01 times x y of x, right? And we can write this in iteration form as, for example, yk plus 1 will be equal to yk plus actually, let's just keep it general for now. We already know it's 0.01, but it's going to be delta x times f of xk and then yk, right? So that is our first order Euler's method in iteration form, and this is going to be true for k greater than or equal to 0. So our initial condition that we're going to start with is going to be equal to 1. And this is because y of 0 was said to be equal to 1. So the first step of the Euler's method will always be exact. That is because we know what y0 is, but we don't know what yk is for k greater than 0, and that's where the Euler's method comes into the picture. So again, y1 will be equal to y0 plus delta x times f of x0 y0. So let's figure out what that is. So y0 is equal to 1. Delta x is 0.01, and then we're going to evaluate our function f, and keep in mind fxy was equal to x squared plus y squared. So this is going to be equal to x squared plus y squared for step 0. And that's going to be equal to, once you simplify that, 0 plus 1, which is 1. It's going to be 1.01. So that's our y1. Once we have our y1, then we get our y2. So again, y2 will be equal to y1 plus delta x times f of x1, y1. So in this case, this is going to be equal to 1.01 plus our step size, and then x squared, and then y squared. Keep in mind, x2 is going to be equal to x1 plus delta x, right? So that's pretty much why we're looking at 0.01 squared, because that's x1, right? Because x0 was 0. So once we have that, and we evaluate that, one can find that that's going to be approximately equal to 1.0202. So that is our y2. And once you have your y2, then you can get your y3. So y3 is going to be equal to, again, y2 plus delta x, f, x2, y2. And once you plug in all those things, you're going to get approximately 1.0306. y4 will be y3 plus delta x, fx3, y3, and that will be approximately equal to 1.0412. And you would, of course, continue this out until you cover your entire domain, right? So we will continue this for the entire domain. And that domain, for example, let's call it D, would be equal to, let's say, x0 up to, say, x final, right? And how many calculations do we need to calculate this? So the number of iterations for this will be equal to x final minus x initial divided by our step size, delta x. So that's the number of iterations it will take to cover that entire domain. So obviously this will take a long time to cover a large interval, but of course that's where, for example, software such as MATLAB or C++ will come into the picture, which of course we'll discuss at a later time. Now let's look at a couple other methods that are actually a little bit better and actually work through another example on how this sort of can come together. So far we've discussed the Euler's method and how it can be used to solve first-order differential equations, but we've proven that Euler's method is a first-order method. So the natural question is, well, can we do better than order 1 method? Obviously it might be more complex, that's probably understood, but what would it look like? So if we sort of follow the same exact idea as our Euler method derivation, we're going to have, for example, y of x plus delta x will be equal to y of x plus delta x times y prime of x, and then plus, so that's our Euler's method there, then we're going to have our delta x squared over 2 factorial times y double prime of x plus o delta x cubed, right? So this would be the second order approach, and this would be a second order Taylor series method. Right? So a first order Taylor series method would be exactly the Euler's method, but this will be the Taylor series method. So if we take the same exact example like we had before, for example, y prime was equal to x squared plus y squared, what would y double prime be? Because we need to figure out what that would be in this example. Because this is y prime, but what's y double prime? So if y prime is equal to x squared plus y squared, so for this you need to generally know implicit differentiation. So y double prime would be equal to 2x plus 2y prime by implicit differentiation. And we know what y prime is, so that's going to be equal to 2x plus 2y times x squared plus y squared, and we can simplify that out a little bit more if we want to. So y double prime will be equal to 2x plus 2x squared y plus 2y cubed, right? So that gives us that particular expression. So once we have that, then we can solve this equation for, y prime or whatever we need, right? So what we have here is y of x plus delta x, right? So that's going to be our y of k plus 1, or I guess you could say your yk. So y of k plus 1 will be equal to, so we're going to have our leading term yk, and then plus, so what are we going to do about this term? So generally speaking, this is going to be equal to delta x times y prime plus delta x squared over 2 factorial times y double prime. But what is y prime equal to? So y prime will be equal to xk squared plus yk squared. And then over here, we're going to have what? So we're going to have delta x squared over just 2 times y double prime. So y double prime. So that's going to be equal to 2xk plus 2xk squared yk plus 2yk cubed, right? So that's going to give you yk plus 1, right? Because notice everything on the right-hand side of this equation is either xk or yk, and the rest is just going to be equal to numbers. But you can continue this for any k greater than or equal to 0, and you will get a second order accurate evaluation, and you can continue this process onwards if you really want to. So why not go up to, for example, third, fourth, fifth, sixth, and seventh order? The downside with this is that we actually need to know what y prime is, because generally speaking, y prime is equal to fxy. But in order to figure out, for example, y double prime, we would have to find the derivative of fxy with respect to x. And generally speaking, this is unknown to us, right? So this is in some sense an implicit method. If we don't know what f is, and generally speaking, we can't write out an explicit representation for an arbitrary f, because this term here and this term here will look extremely different depending on the level of f. So Taylor series methods do give us some insight on how to get better accuracy, but this does have the downside since we can't write a general method for arbitrary f's, sort of like we have for just our Euler's method, which is just the first two terms of that right-hand side. The next few methods that I want to introduce actually do have the advantage of having better accuracy and do have closed form representations for arbitrary functions f. So let's take a look at those right quick. So in terms of closed form algorithms for solving first order differential equations, Euler's method is all we have so far, but we do have some general methods using Taylor series, but we don't have really a closed form representation for finding higher order derivatives of the implicit function f, right? So our goal is to see if we can have explicit stepwise methods for first order differential equations that have higher order than Euler's method. So from here on, I'm just going to be using h instead of delta x just to keep the notation simple. And we know that Euler's method can be represented as yk plus 1, or y in the future, is equal to y present plus h times f present y present. So that's what we have, and we've already proven that this is a first order method. So this also has another name. This is actually called a Runge, so Runge or Runge, depending on, I guess, how you pronounce it. So Runge-Kutta, Runge-Kutta, Runge-Kutta method. And some people often abbreviate this as just RK1 because it's the first order Runge-Kutta method. Okay? What I'm going to do is I'm going to represent this. I mean, we're perfectly happy with this notation, but the next notation is actually going to give us a little bit of insight as to how the other Runge-Kutta methods are going to be represented in terms of formulaic side. So an alternative representation is going to be equal to the following. So we're going to use the notation L1 is going to be equal to f xk, yk, which is just that term there. And then we're going to say yk plus 1 will be equal to yk plus h times L1. So first we're just going to calculate what fxk yk is, and then we're just going to substitute that into the equation yk plus h times L1. So why do we represent it this way? So it gives us some structure that we're actually going to expand upon, because the next method that I want to introduce is what is referred to as a Runge-Kutta 2 method. Now it's not the only Runge-Kutta order 2 method. So sometimes people will refer to this as the midpoint method. Right? So it's called the midpoint method, which is going to be an RK2 method. So the RK2 method, or the midpoint method, is implemented as follows. So L1 will be equal to f xk yk, just like above, and then we're going to have an L2, which is going to be equal to f xk plus h over 2, and yk plus h over 2 times L1. And then we're going to have yk plus 1 will be equal to yk plus h times L2. Notice that since we're working with an RK2 method, notice that we have two preceding things to calculate before we calculate our yk plus 1. Right? Now you could write this in expanded form if you just substitute these things into each other. Therefore, you can write this as, for example, k plus 1 will be equal to yk plus h times f of xk plus h over 2, comma, yk plus h over 2 of f xk yk, double close parentheses. Notice that we have an f inside of an f. Now you may be wondering, where does this come from? Now that I will not prove to you. It does require a little bit of Taylor series manipulations in the higher order spectrum to prove where this comes from, and also the order of accuracy. So I'm just going to state the method here and also state this theorem. In particular, the RK2. So the RK2 is an order 2 accurate method. So it's a lot more accurate than the Euler method for the same exact value h. So if you use an h of 0.01 for an Euler method, aka RK1, and an h value of 0.01 for an RK2, RK2 will typically produce a lot better values than the RK1. So therefore, if you have these values of 0.01 for RK2, you would have to have a value, for example, of 0.001 or maybe even smaller in order to get the same exact accuracy as this RK2 method. Right? So that's pretty much what we mean by accuracy. So that is our RK2 method, and there of course are RK3 methods, and there's several of those, but what I'm actually going to do is jump all the way to RK4. And there is some theoretical reasons which I won't get into here, but RK4 is usually the go-to method for solving basic equations, unless you want to be fancy with your methods. So RK4 is going to have 4 L calculations. L1 is going to be the same as the previous ones, so that's going to be equal to fxk yk. L2 will be equal to xk plus h over 2, yk plus h over 2 L1, same as the RK2. Then we're going to have our L3, which is the same as L2, except instead of L1, it's going to be L2. And then L4 is slightly different. It's f of xk plus h, and then yk plus h times L3. So no over 2's. So notice that we have 4 of those. And then finally, yk plus 1 will be equal to yk plus a weighted average of those L's. So L1 plus 2L2 plus 2L3 plus L4. Notice that these coefficients, 1 plus 2 plus 2 plus 1, all equals 6. And variations of those coefficients actually lead to some other RK4 methods. So you sort of see where a lot of people can sort of play and create their own maybe, but we're not going to get into Runge-Kutta theory here. Right? So that is the RK4 method. So keep in mind what we usually start with. We usually start with a y prime is equal to f x y with initial condition yx0, y0. So if we replace all these xk's with x0 and yk's with y0, we know every single thing in these equations, and then once we substitute them all into that, that's going to give us y1, and then we recursively go through those calculations to cover our entire domain. So let's just close out this video with a nice numerical example, the same exact equation as before that we did with the Euler method, but instead of RK1, let us go through the RK4 calculations to sort of see what we have going on there. So again, let's reintroduce this nonlinear differential equation with the same exact initial condition. We're going to be using the same exact domain step, h is equal to 0.01, but we're going to be using this RK4 method. Now keep in mind there are many RK4 methods. The one I've presented to you is sometimes referred to as the classical RK4 method, but if somebody just says RK4, you can probably be safe to assume it's this one. All right, so we're going to be using an RK4, so first off, let's identify what our f is. So fxy be equal to x squared plus y squared. We know that x0 is equal to 0 and y0 is equal to 1. Once we know all that, and we know the numerical method that we're going to use, then we're ready to go. So the first thing for RK4 is we're going to calculate our L1. So our L1 is going to be equal to f of x0, y0, which is going to be equal to, so we're going to evaluate this, so 0 squared plus 1 squared, and that's going to be equal to 1. Then we're going to calculate our L2. Our L2 is going to be equal to f of x0 plus h over 2, and then y0 plus h over 2 times L1. Once you plug in all those things, you're going to have 1.01005. Then we're going to have L3, which is going to be f of x0 plus h over 2, y0 plus h over 2 times that L2 we just calculated. That's going to come out to approximately 1.0101510. And then we're going to have L4, which is going to be f of 0, or say x0 plus h over 2. It's 0 in our case, but let's just keep it general. So x0 plus h over 2, y0 plus h times L3. No h over 2's. So let's just catch that mistake before we proceed. All right, so no h over 2's in the L4. And that's going to come out to approximately 1.020405. Right, so now we have our L1 through L4. Once we have our L1 through L4, now we can approximate L1. So that means y1 will be approximately equal to, again, y0 plus h over 6. So classical R4 is L1 plus 2L2 plus 2L3 plus L4. And once you plug in all those numbers and you didn't round too harshly, you will get approximately equal to 1.011802. Right, which is a lot more accurate, actually, one can verify, than that y1 that we got for our Euler method. All right, so next we're going to move to y2. So y2, we need to figure out, okay, well, what is x1? So x0 is going to be equal to x0 plus 1 times h, right? So that's going to be what we're going to be plugging in for x1. And the y1, we're going to be using the value up there. Hopefully you didn't round that too much. So what are we going to do? We're going to calculate our L's again. So again, L1 for calculating y2 would be equal to f of x1, y1, which will come out to approximately 1.0238. L2 will be equal to f of x1 plus h over 2, y1 plus h over 2 L1. That will come out to approximately 1.0344. L3 will be x1 plus h over 2, y1 plus h over 2 L2. That will come out to about 1.03445. Not 445, but 45. And then L4. So again, L4 does not have any over 2's. So x1 plus h, y1 plus h times L3. That will come out to approximately 1.0452. Once you have all of your L1 through L4, then we're going to have that y2 will be approximately equal to y1 plus h over 6 So this is practically the same, except y0, instead of y0, we're going to have y1. Again, same weights. L1 plus 2L2 plus 2L3 plus L4. And once you plug in all those things, you're going to have approximately 1.022146. And one can verify that that is a lot more accurate than the Y2 we got for our Euler method, right? So it's very easy to see. It's better to use software, MATLAB, C++, Python, R, whatever you want to do. If you want to compute, Y1 through Y500, because this is definitely going to take a lot of time by hand. So once you're comfortable doing this by hand for 1, 2, 3 or so iterations, you're probably mature enough to code it in whatever language works for you, right? But that is how you can do some numerical methods: Euler, midpoint, RK4, and also some Taylor series methods that are pretty easy to derive on your own as long as you know what f is ahead of time. So now you can approximate the solutions to any first order differential equation, no matter how complex it may be, and you also have control over your error because you can make h as small as possible. Hope you enjoyed this video, and I'll see you in the next one. Take care.